Hi, my name is Ben Chapman and this is my presentation, Turbulence with OpenFOAM. Okay, so here's what's in the presentation. Firstly, I'll talk about computational fluid dynamics and the necessity of HPC resources. Then I'll discuss my project, what the aim was and how I went about achieving this. Then I'll discuss the main results of my project and end with a conclusion. So why CFD and HPC? CFD is used to improve our understanding of everyday systems. An example is the research done by the vacuum manufacturer Dyson, in which they use CFD to simulate airflow over carpets and into the vacuum. It's cost effective to run such simulations, as to set up the experiment may take time and prove to be very costly. For instance, one may require a large wind tunnel. Instead of spending so much time and money on this, one can run simulations to predict things, and if the results are interesting, then an experiment can be undertaken. CFD almost always requires high-performance computing resources, as the problems are usually large. To put that into context, during this project, I ran one simulation using 200 cores, and it took about 12 hours to complete. Had I ran this in serial on one core, it would have taken somewhere in the region of 3 months. Obviously, with such a long time scale, no real work can be achieved. OpenFOAM. So OpenFOAM is an open source code, meaning it's free and anybody can contribute to it. This is especially useful as it enables the user to customize the code to their own needs. For this project, my task was to investigate turbulence models within OpenFOAM for different geometries. The geometry I used was a barrier inside a wind tunnel. This was done for 3 different configurations, with the barrier making angles of 90, 60 and 45 degrees to the horizontal. Meshing. The starting point for most CFD simulations is to create a mesh of the geometry. Except for very simple cases, the equations that govern fluid flow cannot provide analytical solutions. The flow domains are therefore split into thousands of subdomains. The governing CFD equations are then discretized and solved inside each of these subdomains. On the screen, you can see the mesh used for the 90-degree barrier configuration. As you can see, the barrier inside the wind tunnel looks almost a solid white. This is because it is split up into many more subdomains compared to the surrounding wind tunnel. The reason being is that this is where most of the physics happens, so the solution must be as accurate as possible. Solvers. The principal equation that must be solved in order to calculate flow variables, such as velocity and pressure, is the Navier-Stokes equation shown on the screen. OpenFOAM has a variety of solvers to do this. These are the 3 I used. Potential foam is used to initialize the problem by means of generating starting fields. Simple foam is a steady-state solver for incompressible flow. Incompressible means that the density remains constant, so the Greek letter rho in the equation shown on the screen doesn't change. And steady state means the flow variables only change with position, not time. So the first term in this equation disappears. Simple foam is useful in order to get an initial picture of what is going on, but to get accurate physics, i.e. accurate force calculations, a transient solver which evolves the system in time must be used. This is pimple foam. Here is a video showing the result of the simulations for the 90-degree barrier. What you can see on the screen is the system evolving in time. The colours represent the velocity of the wind at that point. You can see that the velocity just in front and behind the barrier is slow, as one would expect. The velocity between the gaps in the barrier is high, as the wind is being sucked through these points, creating a vacuum effect. The highlight of this project were the lift and drag force calculations around the barrier. These were calculated in OpenFOAM and compared to experimental data and data obtained using the commercial CFD software ANSYS. This data had been previously obtained by my mentor Mario. Here is the drag force on the barrier. Here, BC1, BC2 and BC3 refer to barriers at angles of 90, 60 and 45 degrees respectively. As you can see, OpenFOAM gave reasonable results, but they were not as close to experiment as those obtained using ANSYS. It can also be seen that as the angle the barrier makes with the horizontal decreases, the result deviates further from experiment. A possible explanation is the relative mesh quality of the three different configurations. As the angle decreases, the meshes become more difficult to accurately construct. OpenFOAM is very sensitive to mesh quality, much more so than ANSYS. So simulations using low quality meshes are likely to yield results less accurate than those obtained using high quality meshes. I should say at this point that the same mesh files were used for both ANSYS and OpenFOAM. Here is the lift force, and as you can see, the OpenFOAM results look much better. For the most part, OpenFOAM actually gave results closer to experimental data than those obtained using ANSYS. Again, it can be seen that the deviation away from the experimental data becomes more pronounced as the angle to the horizontal decreases. So to conclude, 3 different barrier configurations were simulated. The lift forces calculated using OpenFOAM were pretty good, the drag forces not so much. Mesh refinement may yield better OpenFOAM results in the future. Thank you very much for listening.